we wind up looking at a non-wall connected set, and if that non-wall connected set has an average elevation that's below the that's below the floor average, and it's a child, then it's a courtyard, because I mean the roof of a building isn't going to drop below the ground. That doesn't make any sense. So that's a heuristic we're able to use there. The ramp problem is what the question was asked about. In the ramp problem, what happens is you have two scenarios. The first scenario is, okay, the ground bleeds on top of the building, and then now we want to say, okay, the ramp connected the ground to the top of the building, but we want to reclaim that as building. It's not necessarily ground. So we look at the top of a wall-connected set here, and we say, hey, the top of the wall-connected set, let's do region growing. We know the floor average of this wall-connected set, and as we do region growing, make sure these triangles have average elevation greater than that floor average. The problem is what if this wall-connected set isn't on the side of a building? Let's say it's on the bottom of a ditch. Then at the top of that ditch, of the wall on top of that ditch, you're still going to have a non-wall connected triangle that's adjacent to it. And as you do region growing, you'll come into contact with a whole bunch of different wall-connected sets. That's a property of the ground. The ground is going to have lots of buildings on it. So if you come in contact with more than 50 different wall-connected sets, we say, hey, that's probably in that scenario, you're growing on the top of a ground. In this scenario, you're not going to come in contact with 50 different wall-connected sets because you're on top of a building. The building isn't going to have 50 distinct walls. Okay. Well, you won't start when you do the region growing here. You're going to do it like you'll look at, see, here's the wall connected set, and you'll do the adjacency to the top of the two highest vertices within the triangle. So you're making sure when you look at the triangle that's adjacent to that wall-connected set, you look at the two highest vertices in elevation. Otherwise, if one of those vertices is the lowest in elevation, then you're growing on the bottom of the ground. That's that added constraint, is when we say, okay, if you're looking at a wall-connected set and then look at the triangle adjacent to the top of the two highest vertices, then you'll do the growing here as opposed to on the bottom of the ground. The reason why you'll grow the ground from the bottom and up the ramp is when you start out initially, you look at for the triangle with the lowest non-wall, you look for the non-wall triangle with the lowest elevation average. So then you'll be on the ground and you'll wind up growing the ground, and as the ground grows, it'll grow up the ramp and on top of the building. And the reason it'll grow up the ramp is because this is a ramp that leads to the top of the building, you're going to have non-wall triangles seep up the ramp to the top of the building. So that's why a label go up the ramp and the top of the building, and the building will be initially, the top of it won't be ground. The reason we still know this is ground, though, is because this is connected with the rest of the ground, and the rest of that ground will have a lot of immediate wall-connected children protruding from it. Even if you wound up picking on top of the building, let's say you picked on, lower left corner here. Well, if this terrain is divided, then you're right. It still could be a problem. But I mean, the problem is as you grow, you're going to grow up the ramp. So you grow around the building. As you grow around the building, you'll grow up the ramp. The location doesn't necessarily. The reason why we start at the bottom is because we want the tree to form with the ground and then up. If we start at the top, then it would be the formulation of the problem would be different, and we wouldn't be able to employ a lot of the heuristics we would, which is why we have to be greedy in that decision. Any other questions? Oh, do the other algorithms have trouble with the smaller buildings? I recall, no, actually Metainican and Wasselman didn't do this metric. No, excuse me. Metainican did, Wasselman didn't, and so did Rottensteiner. Metainican also, his performance for the smaller buildings, if I recall correctly, was a little bit worse than this algorithm's. Rottensteiner's was a little bit better because when it came to the smaller buildings, he was able to extract and use features from the aerial imagery to distinguish the smaller entities as whether or not they were vegetation. So when you're running into those smaller areas, it's like, is this guy, he's pretty small, he's probably vegetation, but oh no, he could be a shed. And if you have the multispectral aerial imagery, you can wind up pulling like a greenness index from that. His method is pretty good too. He'll use the data as it is available, and he'll develop probability mass functions out of that. And he'll say, okay, here's characteristics of buildings, and they have like first and last return differences that are low, and they have first and last return, and then the vegetation has first and last return differences that are high, and he'll form a probability mass function out of just first and last return differences. And then he'll form a probability mass function out of a greenness index extract from the image. And then he used Dempster-Schaefer theory to wind up incorporating all of those probability mass functions to incorporate a classification for the buildings. So he is able to realize the data as it's available with that Dempster-Schaefer theory, which is interesting. But again, his method wants the registration of those sets together before it can proceed, so that when you say this is a pixel, it corresponds to the same area in the LiDAR data. I see what you're saying. The buildings. I didn't necessarily use that. I have seen it used. Ulrich Newman and his student actually make use of that. You'll notice, like for the suburban areas, oftentimes the buildings are parallel with one another, and sometimes the houses themselves are parallel with one another. And I've seen morphological filtering approaches, as well as Newman-Ulrich. They'll calculate vectors based on certain attributes of the data, and if they notice parallelism, they'll wind up exploiting that as a means to identify it. So it has been used. I wasn't able to use that, but that's certainly a valid point. Any other questions?